we can parameterize the curve x squared plus 4y squared equals c. There are many ways to parameterize it. One way is to let x of t equal square root of c cosine t, y of t equals 1/2 square root of c sine t. Just a standard parameterization for the ellipse. It would look a little more standard if we let our constant be c squared. There'd be no loss of generality in doing so, then we wouldn't have this square root to carry around, but it's really not a problem to do so. And we'll just arbitrarily confine this to one cycle of the ellipse, one path that goes around the entire ellipse by letting t go from 0 to 2 pi. We could, of course, have done this as the cosine of 2 pi t and the sine of 2 pi t, where t goes from 0 to 1. And there are a lot of other parameterizations we could use. We could let x equal t so that y would equal 1/2 square root of c minus t squared. No matter what parameterization we use, if it accurately parameterizes the curve x squared plus 4y squared equals c, we're going to get the same result, even though the steps might look different. Now all we do here is we simply have this parameterization so that now we regard the ellipse as being traced out by the tip of our r vector, and our r vector is just xi plus yj. X is x of t square root of c cosine t, y is 1/2 square root of c sine t, so that r prime of t, remember, is tangent to the curve defined by r of t, so this is going to be a tangent vector. So this is going to be tangent to the curve. And of course we could divide this by its magnitude and get a unit tangent vector, but that's not necessary to illustrate what we're trying to illustrate here. So our tangent vector, our r prime vector, is this. Our gradient vector, as we've seen, is 2xi plus 8yj. Substituting these expressions for x and y into the 2xi plus 8yj, we get this, and that's equal then to this. And the arithmetic is very simple. The only change between here and here is I've multiplied 8 by 1/2 to get 4. Now, I'm not going to go through the details. It would take time and really be unnecessary. If you do the dot product of this del f vector here with the r prime of t vector here, well, let's just look. We got the cosine, the I components. The cosine matches up with the negative of the sine. The sine matches up with the cosine. So we've got like a negative sine times cosine plus a sine times cosine. The numbers, we're going to have a factor of 2 square root of c and another square root of c here, and a factor of 4 square root of c and 1/2 square root of c here. Both of those factors then are going to be 2c, so that the dot product is going to consist of two equal and opposite terms, each one being 2c cosine t sine t, or its negative. And that gives us the desired predicted result that del f is perpendicular to the tangent vector.